Inclined planes represent any situations where an object is interacting with a sloped surface. This could be a moving ramp, a ski slope, a slide, and many, many others. If we start with a generic box at rest on a ramp that is inclined at angle phi, let's think about the different forces that could be acting on the box and how they must be oriented. There can be no tension force because there is no rope, chain, or other such object attached to the box. Gravitational force is always acting toward the center of the Earth, and a normal force is acting perpendicularly out of the ramp supporting the box from falling straight down. From these two forces, we can see that there is a net force acting on the box downwards to the left. So what is preventing the box from sliding? There must be a frictional force holding the box in place that counters this net force. And since friction acts parallel to a surface, we know it must be acting backwards up the ramp. Now our diagram shows a net force of 0 acting on the box. Now let's show our forces as a free body diagram so that we do not have to worry about the ramp or the box. Since the friction force acts along the surface of the ramp, its angle relative to the 0-degree line is phi. Our model for a box at rest on a ramp is now much simpler, but we can actually make it even more simple so that we can mathematically analyze it better. Right now, we have the gravitational force directed perfectly vertically so that it has no horizontal component. The normal and the friction forces have both vertical and horizontal components. We can actually tilt our diagram to make it so that only one force has both vertical and horizontal pieces. Since the normal and the friction forces share a 90-degree angle between them, we can tilt our diagram so that they lie along the vertical and horizontal axes respectively. By doing this, we are essentially saying that our x dimension lies along the surface of the ramp, and the y dimension acts perpendicularly out of the surface. Now, only the gravitational force has both vertical and horizontal components. The normal force acts only in the positive vertical direction, and the friction force acts only in the positive horizontal direction for our system. It should be noted that since we are using an angle that is not the standard angle for the gravitational force, we are actually going to use the sine function to find its horizontal component and the cosine function to find its vertical component. We also need to manually identify them as negative values when we set up our givens list. Let's now mathematically analyze inclined planes. Since the box is at rest, we know it is in equilibrium, so we can begin with Newton's second law equilibrium statement, or F net equals 0. We can then begin working with one dimension at a time, so let's start with the horizontal dimension. The net force horizontally is equal to the sum of all the horizontal components of the three acting forces. From our identified values found using the previous free body diagram, we can substitute in our horizontal quantities. Finally, we can simplify as much as possible, and we end up showing that the frictional force acting backwards up the ramp must be equal to the component of the gravitational force acting downwards along the ramp. We can then go through the same analysis in the vertical dimension, but substituting different zeros and other quantities that were identified before, and we end up showing that the normal force acting upwards on the box must be equal to the component of the gravitational force acting downwards into the ramp. The mathematics of inclined planes becomes much easier when we tilt our free body diagram. When you do this, make sure that you carefully analyze which forces are positive and which are negative, as well as which trig functions to use when decomposing the vectors.